Now that we've established some rules with simplifying radicals, we can expand that and see how those radicals are related to what we call rational exponents, which basically means exponents using a fraction. Our key concept is telling us that if I was to treat a radical instead as an exponent, I know that the power is going to act as the numerator, so top part of my fraction, and then the root that I'm taking, if I'm taking a root for a radical, is going to end up on the bottom of that fraction. So something like a square root, that would be a first power and a square root, making 1/2 as an exponent. Cube root, I have a first power and a cube root, which make 1/3 as an exponent. That means if I want to simplify each expression, if I take something like 27 to the 1/3, that's like saying if the power is 1, I'm taking 27 to the first power, and again, the denominator of that rational exponent would be 3, that would be the index, so that would be a cube root. That means if I'm looking for just the cube root of 27, I want to simplify this further. We know that 3 times 3 times 3 gives us 27, so that cube root would be 3. If I was to apply that same kind of concept, again, if I was to use the numerator as a power and the denominator as a root, looks like we're taking the cube root of 3, can't really simplify that. But then if I bring in the cube root of 2, again, also saying 2 to the first power, I can multiply these since they have the same index to get the cube root of 6. That's as simplified as I can get because 6 doesn't contain any perfect cubes, but I do want to make sure we can combine those together as a single radical. Last case, if I take 11 to the 1/2 power, again, that's basically like saying the square root of 11. We could put a 1 for a power, we could put a 2 for a root, but we don't need those if we're just expressing a square root. Same thing with another square root of 11. And this is a handy trick to know that if I multiply a radical times itself, that does cancel the radical, because if I multiply those and I get 121, that is a perfect square root. If I was to try that with a few more questions, or if you were to try it rather, I think it's helpful to know on this first example that 216 is a perfect cube. 216 is just 6 to the third power. So if I'm taking then the cube root of 216 rather, I just get 6 as a result. Kind of like just taking the cube root of 27 since that was also a perfect cube. We also want to make sure we can do rules like with last time. If I have 125, I can express that differently in its lowest terms. So 125, another perfect cube. But now that I'm looking at a fourth root, so 1/4 as a rational exponent, I want to make sure I can use the rules from the last section, combine those powers together. I get 4 total powers of 5. And then if I'm taking a fourth root of a fourth power, that just simplifies to give me 5. And last case is kind of like the example we saw from above. 1/2 power is just a square root, so square root of 7, square root of 7, I just get 7 when I multiply those together. So in our next section, we're going to be doing some very basic conversions with a variable rather than with a number as a base, but still works the same way. Again, you want to think of the top as a power and the bottom of your rational exponent as a root. So then if I want to write this in radical form, top is a power, bottom's a root, bottom's a root, not just a fraction again. X squared, this is going to be a cube root of x, and that's as simplified as I can get. Again, I can't do any simplifying with that radical. I don't have enough powers to remove outside of that radical sign. It is also good if I see a decimal as a power to think about what that would look like as an exponent, or as a fraction rather. 0.2 is the same thing as 1/5, so then if I'm still treating that numerator as a power and the denominator as a root, this looks like it's just going to be the 5th root of x. I should be able to go the other way around, so again, if that rule still applies, the power goes on the top of my fraction. That would be x to the 3rd power, and then if it's a 4th root, I just put that over 4. X to the 3/4 would be the first example, and then doesn't matter if the power is outside. We see this rule up above that I could write the power inside, outside, not going to matter. Either way, that's still y to the 4th power, and with a 5th root, that gives us y to the 4/5 as a rational exponent. Trying that a couple more examples, again, see if you guys could solve those before I unveil them, but first one, rather simple, like we saw from above. Top is a power, bottom's a root, so 3rd power, 4th root. And next time I do want to make sure I can also simplify that as a fraction, because rational exponents means I need to be able to figure out what's the power, what's the root. So if that 0.3 can be written as 3/10, that's x to the 3rd power and using that 10th root. So trying that again with the next couple examples, if I took a 4th power and a 3rd root, now we're just going the other way around. So 4/3 as a rational exponent, 3rd power 7th root just means that's going to be 3/7 as another rational exponent. So before we start our next example, it's good to review some properties of what I can do with these rational exponents. And some of these we've used before when simplifying radicals, some of them we just haven't addressed yet. The first that we've seen before, if I multiply 2 powers using that same base, I can just add the exponents together. Given an example using, again, a rational exponent would work, even if it was not a whole number for our exponent. I could also take a power to another power. That means I'm going to be multiplying rather than adding. And again, I could also basically think of distribution as a power. So if I have 2 bases and I'm using the same exponent for both as a grouping, I know I can use both of those with that same power. Another rule to remember is that if I have a negative exponent, I can rewrite that as a fraction. So let's say if I have negative 1/2 power, that's like writing 1 over the 9 to that 1/2 power. We've seen this rule before when I was trying to combine radicals. Again, if I have the same base on the numerator and denominator of a fraction, instead of using addition as we would with multiplication, I'm going to be using subtraction, and it's always going to be the numerator minus the denominator for that power. And we also can use distribution even if I'm using a fraction. So a over b just means I distribute to get a to the whatever power I'm using, and then b to whatever power I'm using, much like if I was just distributing to a product. So now if I'm looking to apply some of those properties, it's going to be easier to rewrite some of these expressions as rational exponents, because if I'm dealing with fractions, they're much easier to combine than trying to think what's happening with my square and my cube roots now that I'm looking at a different index. So I'm going to rewrite the numerator of my fraction using a rational exponent. Again, if 3 is the power, x to the third, and then if 2 is the root, again, kind of hidden in that index, but that's a square root, so 2 is our root. That means that would be the numerator of my fraction. And again, since I'm using division rather, division is going to follow this principle that I'm taking the power from the numerator of my fraction, subtracting the power from the bottom. So if I figure out this power of x, notice that they are the same base, x and x, it looks like it's going to be a second power and a third root. So since I'm using division, I'm going to be subtracting the power from the top, subtract that power from the bottom. And that means I just have to figure out what's going on with combining these fractions. This is going to be pretty consistent in a lot of our work. We want to make sure that we're combining to get the same base. So if I express these both in terms of 6, multiply the first one by 3 over 3, so I get 9 over 6 rewriting the first fraction. I get 4 over 6 rewriting my second one. Again, just like with any other fractions, we have to get them into the same base to be able to add or subtract. I know that if I subtract 9 minus 4, I then just have 5. So if I get x to the fifth 5 over 6, I just want to rewrite those as a radical again. So if I have 5 as a power, 6 as a root, sorry, I was going to write that as a fraction again, 5 as a power, 6 as a root, this would be my final answer after I was able to combine top and bottom. Trying that again, if I use multiplication, it's not really going to change our rule too much. We just have to know if I take that first power, 1/2 is a square root. Second one, if I'm using a cube root, this would just be 1/3. And again, now that I'm multiplying those two together, I'm going to be adding those powers rather than subtracting. Again, that was the case where I was using division on the last question. And same thing here, if I want to be able to combine those fractions, just want to get them into a common denominator. So it looks like 3, 6, and 2, 6. This, it looks like, is going to give us another 7 to the 5, 6 power, which means we can also write this as a similar root. 5 is a power, 6 is a root, and that's going to be my simplified form. Trying that with a couple more examples. Again, you guys are free to try these first. It looks like our next example is division, so we want to be thinking subtracting powers. If I take the power from the numerator, again, 3 is the power, 4 is the root, 3/4. If I take the denominator, 2 is a power, 8 is a root. Notice that it could also simplify first, but I just chose those to leave as a base of 8. Get those to be the same denominator if I want to subtract those fractions. Again, subtracting because I'm using division rather than multiplication with those two bases. And I do want to make sure I simplify my answer completely. So if I get something like 4/8, I know that's 1/2. I know that 1/2 is also just the same thing as a square root. So example D for the last one should also follow kind of like example B that we did with those 7s, because this case is, again, another situation where I'm going to be adding the powers together because I'm multiplying those bases. Again, multiplying would be adding the powers. Division, like that last example, is when I subtract. So if I get square root, that's a 1/2. If I get a 4th root, that's a 4th. So if I add those fractions together again, getting that common denominator, I get 3/4. 3 is a power, 4 is my root. I would also say for something like 3 to the third, since that's a small enough power, I wouldn't say that you have to write out 7 to the 5th or memorize what that would be, but it's always good to know these small cubes. 3 to the third power just makes 27. So for that simplified form, I would just rewrite that as the 4th root of 27 rather than 3 to the third. And now we're just going to be applying another property when I'm trying to rewrite these in the simplest form. And that means if I have something like 32, it's going to be good to recognize 32 as a relatively low power of 2. If I take 2 times 2 times 2 times 2 times, forget how many times I said that, but it should be 5 times I multiply 2 together. I think 2 to the third is 8, 2 to the fourth is 16, so 2 to the fifth is going to be 32. Again, kind of a good one to just know. I know that I could express it this way instead. We're taking that base 32, rewriting it as 2 to the fifth. And now we've seen the power, or the rule from before. If I'm taking a power of a power, this time is a case where I'm not adding the powers. Instead, I'm just multiplying those together. So if I get something like 5 times 3/5, I can use my same tricks with any other fraction. I can cancel the 5 with a 5. That just leaves 2 to the third power. And again, something as small as 2 to the third power, I can just simplify that as 8. Taking another similar step, again, if I have 16, it's good to recognize this as a power of 2. 2 to the third would make 8, so one more would make 2 to the fourth for 16. And if I use the same idea as before, if I take 4 times, or sorry, I would write that as a fraction, 4 over 1 times 3 over 4. Since I'm taking a power of a power, as we've seen from those rules from above, I can multiply those rather than add them. Again, the 4's cancel. I'm just left with 2 to the third. So this looks like another answer that just simplifies to give me 8. So now we have a negative exponent, but it's not going to change our work too much. I would just take the step to, again, as we've seen from before, write these in its lowest terms. You never know when that's going to help cancel something out. 3 to the second power. And again, if I have something like negative 3.5, it's not going to help us too much if it's not written as a fraction. So I'm going to rewrite that as negative 7 over 2. And that's going to tell me, again, if I have a power and a root, I can rewrite that later at the end of this question. But let's multiply as we've done from before. 2 times negative 7 over 2. Again, the 2's cancel as they have on some of those other questions. And if I just am left with something like 3 to the negative 7th power, this is the one case where I have to remember a negative 7th power, as we've seen from those properties from before, is just going to write this as basically sends it to the denominator of my fraction, or sends it to the opposite side of my fraction. And now instead of 3 to the 7th, I just have 1 over 3 to the 7th. And again, something as large as 3 to the 7th, I wouldn't say that we have to memorize it, so I'm fine leaving it in that form. If this was like 3 to the 3rd, though, I'd say I'd write that as like 1 over 27, for example. A couple ones to practice with. This is also, again, where it's helpful to know these as lower powers. We know 32 is 2 to the 5th power. Even if it's negative, not going to change our result too much. I didn't really show my work for that part, but yeah, I was just multiplying 5 times 4 over 5. That cancels the 5's again, just gives me a 4th power. This is also where it's helpful to remember that even though I start with a negative, if I'm using that even power, negative 2 to the 4th power, multiplying an even number of times, that still will give me a positive 16. And trying that one more time, it looks like if I take that decimal as a power again, kind of like with our last example from above, I know I can rewrite 16 as 2 to the 4th. That's going to help me with some cancellations. I can rewrite negative 2.5 in that rational exponent. That's going to allow me to multiply with my fractions. In this case, it also could multiply like 4 times negative 2.5, and that would give us the same kind of exponent. So calculator would also be fine if I wanted to multiply those two. But yeah, just as what we've seen from before, if I get a negative exponent, that means I'm going to rewrite that on the opposite side of the fraction. So it looks like 1 over 2 to the 10th rather than just 2 to the 10th. And again, this is a large enough power, I wouldn't have to worry about writing that power out. Next few problems may seem kind of tricky, but it's the same rules as before. So all I want to do is re-express the, looks like inside of this fraction in its lowest terms. That means I could just rewrite 9 as something like 3 to the 2nd power, x to the 4th power stays. And since I want to be dealing with these rational exponents rather than using radicals, I'm just going to re-express the square root of y, again, power on top, root on the bottom, as just the 1/2 power. And now if I'm taking these all to the 3/2 power, we saw a rule from earlier that said I can distribute this power to everything on the inside of that fraction. So all I'm looking to do for, let's say, like the power of 3, it was, 3 is using that 2nd power. I can multiply that power from the outside. It looks like that just cancels and gives me 3 to the 3rd power. If I do the same thing with x to the 4th, 4 over 1 times 3 over 2 again, this is going to cancel, it looks like, and leave me with x to the 6th. And since I re-express that radical instead, sorry about that. Since I expressed that radical instead for the y as 1/2, that's where I can also do 1/2 times 3 over 2. That's just going to give me y to the 3/4. One thing I want to finish this question with, though, is I want to rewrite that in a radical form. And something like 3 to the 3rd, again, a small enough power I can use as just something like 27. X to the 6th is going to stay, but since I'm using a rational exponent, we don't want to use those for a simplified answer. That's not x, sorry. That's going to be y to the 3/4 power. So y to the 3/4. 3 is a power, 4 is a root. This would be my simplified version now that I've distributed that exponent. If I'm looking to solve the other one, looks like I'm going to take some similar steps. It looks like 2 to the 4th is going to give me 16. Y to the negative 8th is already in good form to be able to combine later. So now if I just distribute that power again, 4 over 1 times negative 3 over 4, 4's cancel. I'm just left with 2 to the negative 3rd. And if I take negative 8 times negative 3 over 4, see what happens there. It looks like I get negative 2 times negative 3. We do want to watch out for negative times negative giving us a positive, but if I have something like 2 to the negative 3rd power, remember that's going to go to the bottom of my fraction, and 2 to the 3rd, again, also a small enough power, I would be able to just simplify that as 8. So y to the 6th over 8, final answer. Y had a positive exponent after I multiplied. 2 had a negative, so that's why that ended up on the bottom. Trying that one more time with your example. Looks like if I had 8, again, that's just another power of 3 that I could use. I could re-express x. We want to be careful about x. You can say it's like 1 and 1/2 powers, but that's easier as just a rational exponent, 3 over 2. Y, since I'm taking a square root, also 1/2. And now if I distribute that power, I didn't really show the work for it again, but distribute for the 3 times 2/3. 3 over 2 times 2 over 3 just cancels because that's reciprocal. And 1/2 times 2 over 3 also gets me 1/3 for y. Last step is just want to make sure, again, -2 if it's an even power, that gives us a +4. X to the first, simple enough, we just get x. But then also y to the 1/3, we do want to re-express that using our radical.